In this lecture, we're going to learn to predict the mass of products. More commonly, I'll refer to this as stoichiometry. Okay, nothing new there for us. In this lesson, we're also going to talk about limiting reactants, and then we'll wrap it up with percent yield. Okay, so getting into this, how we will commonly even start out in this course, expectations are of course higher with it being AP. Given just this sentence here, you would need to come up with this balanced equation. What mass of water can be produced when a car burns 246.4 grams of methane? Okay, so if we're not given this equation, you need to know that this is methane, oxygen as part of this combustion reaction. Do you remember your combustion reaction? And then what's always produced in a combustion reaction when you have a hydrocarbon? Well, it's always carbon dioxide and water. So you need to know how to write out even this. And in the course, you will have to do this. So we're given this unbalanced, and so we're going to have to balance it. The way I like to do this is underneath the arrow, I write out all the elements. We have a carbon, a hydrogen, and an oxygen. So there's one carbon here, it's on the left side, so we put one over there. We have 4 hydrogens, 4 on this side, we have 2 oxygens. Okay, we come over here, we have 1 carbon, we have 2 hydrogens, and then we have, notice you have oxygens split up, or it's in more than one compound. So we have 2 there and 1 there for a total of 3. Whenever you have an element that's split up between 2, save it for the last when you're trying to balance it. Well, our carbons, they match up 1 to 1. Okay, now we come to our hydrogens, 4 to 2. So something needs to be done. All we can change is our coefficients. This is a subscript. You cannot change a subscript. Okay, you change subscript, you totally change it. Okay, so we can only change the number in front here. We have 4, we need 2. Well, if we multiply this by 2, we would end up with 4. So we just put a 2 here. 2 times 2 equals 4. Now they're even, but that changed our number of oxygens. So we still had 2 here, but now we have 2 here for a total of 4. Carbons are still good, 4s. Well, oxygen is off. If I were to multiply this number by 2, I could get to 4 as well. So I'll put a little 2 right there as a coefficient. 2 times 2 equals 4. We are now balanced. Okay? So we started with our balanced equation. Now we're going to set up our stoichiometry problem. As you can see in a stoichiometry, like predicting mass, you're only be given one number. Okay? That's the number that you're going to put to the left here. Okay, we'll start out with that. And we have to remember what mass of water. Well, mass is measured in grams, so we'll do grams H2O on this side. So think about that as you set up your equation. So as we said, we had our one number, that's going to go here. And then we said mass of water, grams water over here. I'd like to write that out just to remember where I started, where I'm going. And then we're going to convert between the two. So we have our balanced equation. So we have grams here. Well, we want to get out of grams because everything stoichiometry goes through the mole. Okay, so we have to get out of grams and into moles. We're going to divide by grams. Okay, so those units cancel out, and now we get into, for every 1 mole of methane, CH4, how much does it weigh? Well, this is where you look up each individual part. I have 1 carbon. I look on the periodic table, it weighs 12.01. I have 4 hydrogens. Each hydrogen is 1.01. So 4 times 1.01 is 4.04, plus that 1 carbon, which is 12.01, and that's how you wind up with your 16.04. Actually, I would put it at 16.05. Sorry, the typo there. But we'll roll on with it regardless. So we take this, and we know for every 1 mole of this, it weighs 16.04. And we'll divide the 2. We come over here now. Now you can see that we're already in moles, and we want to convert substances. We want to change from methane to water, because they said what mass of water will come from this much methane. So because we're switching substances, we now, to find our coefficients here, we have to look at the coefficients here. So we look at the balanced equation. We have no coefficient there, or it's assumed to be 1. So that 1, as you can see the arrow, tells us there. Well, we're going to water, so we find its coefficient. The arrow comes down here. So it's a 1 to 2 ratio. Okay, so now we're in water, and we come over here, and we want to get out of moles of water and back into grams of water, because that's where we're ending. So we need to calculate what are the number of grams per mole. Again, you look up 2 hydrogens, 1.01, Oxygen, you have one of them at 16.00 for a total of 18.02 for every 1 mole. Our units, moles of water cancels out, moles of methane cancels out, grams of methane cancel out, and you're left with grams of water, which matches up with where you're going. It's time to calculate. Multiply everything on top, divide by everything on the bottom. Okay, sometimes if you have a graphing calculator, you'd be fine. If you use one of the classroom ones, you have to be careful sometimes. You might need to put divided by, divided by, divided by, because when you start multiplying, sometimes it can mess it up. You arrive at 553.6 grams. Now note the sig figs here, okay? You have 4 there, 4 there. These are ratios and they're assumed to be infinitely exact, so we don't really take those into account. And that's how you would predict the mass using stoichiometry or ratios, measurement of ratios in Greek. Okay? Now I'm going to introduce to you, or remind you from last year, limiting reactants. Limiting reactants are far more functional because this is getting into, again, more real world. Because rarely do you have perfectly amount of two quantities of different compounds that you're going to then react. One of them is going to get used up first. The one that gets used up first is your limiting reactant. Okay? Once it's used up, the reaction stops. It's over. That's it. You're done. Okay? It doesn't matter how much you have of the other one or other ones, which we'll call excess. They're just going to sit there unreacted because you're done. It's compared to you have a whole loaf of bread, but only one piece of meat. Okay? You stop at the sandwiches there. Okay? And so that's what we'll look at. The terms limiting reactant, that's what you run into first, and excess reactant, what remains. We will use the limiting reactant to figure out how much did we actually make. Because once you run out of this, the reaction stops, that's the amount you actually make. So whatever value you had over here, that's what you're going to have. So you're looking for the smaller of the two as you run multiple stoichiometry problems. Okay? For example, what is the limiting reactant when 28 grams of glucose react with 14 grams of oxygen gas? Okay? And the secondary question, what mass of carbon dioxide is produced? Okay? Step 1, write a balanced equation. Yikes. Okay. So we have glucose. You got to dig back into your memory there, and we're going to see that we have C6H12O6. Here's glucose. Okay. And then we're going to say when 28 grams react with oxygen. Now remember, oxygen is a diatomic molecule, O2. If you write just O, it's going to mess everything up. Okay? And what's that going to produce? On this, remember, this is a hydrocarbon reaction. So, of course, what do you make? Carbon dioxide and water. Now we would want to balance it. CHO. I have 6 carbons. I have 12 oxygens, or excuse me, 12 hydrogens, and I have 8 oxygens. Over here, I have 1 carbon, I have 2 hydrogens, and I have 3 oxygens. Okay? Get them even. 6 is, I'm going to multiply this one by 6, and that's going to change that to 6, and that's going to adjust our number of oxygens. We now have 12, 13 of them. Okay? Adjust my hydrogens. I have 2. If I multiply this side by 6, that's going to give me my 12. Okay, now I have 12 there and 6 there for a total of 18 oxygens. Okay, I have 6 over here and I have 2 right there. I can multiply this one out. So if I were to put a 6 in front of this, that would give me 12 plus my other 6, that's 18. 6s, 12s, 18s. There's your balanced reaction. Okay, we are now ready to get into the chemistry. Okay, so on this one, since we came to this, I'm going to go ahead and erase all this. Okay, we can see that. Oh. And so we're going to come over here, and now we're going to take a look at our step 2. Find the mass of carbon dioxide that would be produced by each. Okay, so we have our 28 grams of glucose, multiply. So again, we are converting out, we're going to the molar ratio, so then we can incorporate the ratios found within the balanced reaction. 28, for every 1 mole of glucose, it weighs 180.18 grams. Okay, so now we're in the mole, now we're going to switch substances. Whenever you go from glucose to carbon dioxide, or glucose to oxygen, or glucose to water, you'd have to go by their molar ratios. So we got to moles here. We look in the equation now, we want to go to carbon dioxide. So for every 1 mole of this, I need 6 moles of carbon dioxide. And then I bring it over here, get back into grams, and I go 1 mole of carbon dioxide for every 44.01 grams of carbon dioxide. Multiply it through and you get 41 grams of carbon dioxide. Okay? So that's how much we found for that. Now we need to do our calculations for oxygen. Okay, we did our glucose. Now a given number was 14. So however many numbers are given to you, that's how many stoichiometry problems you're going to run. 14 grams of oxygen. Again, get into your moles. So for every 1 mole of O2, this is actually, you will come to learn that I always blame the Canadian. Okay, this was put together by a Canadian AP teacher. So whenever something's wrong, I blame the Canadian. Okay. So again, grams. Why did I change that? Did anyone else notice that needed to be changed? Well, I had to change that because we did 1 mole of O2. Well, O2, each oxygen, there's 2 of them. Each one is 16 grams. Well, there's 2 of them. 16 plus 16 equals 32. Okay. So now we're here. We go for every 6 oxygens, there are 6 carbon dioxides. Okay, we're good on that. And again, carbon dioxide always weighs 44.01 for every 1 mole. So now we multiply that through, and let's see what we get. I'm going to grab a calculator just to verify all that. All right, we got 14 times 1 times 6 times 44.01 divided by 32 divided by 6 divided by 1. And I got 19.25, so we'll call it 19 based on sig figs. And I'd agree with that. That seems a little more correct. Okay? So that should actually be 19. And yeah, that should, because we would have halved it there. So we actually are dealing with 19. Adjust your notes accordingly. Okay? So I just caught this now, but let's adjust it to this. So now we have 19 being less than 41. Okay? 19 belonged to the oxygen. And over here, that 41 belonged to our glucose. Okay? Well, 19 is smaller than 41. Okay? So that means we ran out of oxygen first. If you run out at first, it's the limiting reactant. The question is, how much was actually produced? How much carbon dioxide was actually produced? Well, it's whichever number is smaller. Again, because they're erroneous number, he said 39. He really meant 19. So we would need to adjust this and say, we did all the calculations. The smallest number we came up with is 19. Therefore, that's how much is actually made. It doesn't matter that we could have made 41. We ran out of oxygen first. We're done. Just like the sandwich making's done when you run out of meat. Well, it's done once you run out of oxygen. Okay? So that's limiting reactants. Okay? This last part, again, we're staying very real world here. Okay? And we'll talk about the various reasons why later. But just because you put 2 chemicals near each other, it's not like, wow, they always react. Okay? And every bit of it reacts. A lot of times you'll get a good reaction going. But it's not always, it's not perfect. Okay? And so there's a question of how much will this yield? Or how much did it yield when you do a reaction? So find the percent yield if only 32 grams of carbon dioxide was produced in the previous problem. Now again, follow me on this one because again, we're working with erroneous numbers and they were assuming that it was 39 grams. Okay? So What you do is you do actual divided by theoretical. Theoretical is what you get on paper. Everything's easier on paper. When you have to go to the laboratory and actually do something, now you're talking about actual. So this saying you made 32, okay? You were expecting 39. 32 divided by 39 times 100, okay? It means percent. That's why you end up with that unit back here, percent. Okay? 32 divided by 39 gives you 82%. That's a percent yield. Okay? That measures your efficiency in doing a process. And this is where money's made. If you can make this number larger, you make more money. So if you can learn ways for your business, hopefully you own it, but if you're working for the man, he'll pay you much more if you can bump this percent yield up. And that's where we'll get into thermodynamics, the Chatelier's principle, all sorts of things of how to drive this number up to get paid more money. Okay? So that's it on this lesson. I hope that makes sense. Sorry about the wrong numbers. Good luck.